Welcome back everyone. In this lecture we will continue with some more examples of representations. So, what we will do, we will consider two-dimensional non-abelian Lie algebra. We denoted it by G2 and then classify all possible two-dimensional representations of that two-dimensional non-abelian Lie algebra. So, here is the problem. Classify all two-dimensional representations of G2. Recall that G2, which is two-dimensional non-abelian Lie algebra. So, which is span of S comma T, where the bracket St is given by T. Okay. So, if we are interested in actually coming up with the representation of G2, then it is easy to see that we have to define a map from G2 to GL of V, where this S will be mapped to some capital S and then T will be mapped to some capital T. Because this map is determined by capital S and capital T, we can denote it by S comma T. So, these two matrices S and T should be chosen so that the bracket ST should be equal to T. So, now phi ST isomorphic to phi S dash T dash if and only if again there exists some GL invertible 2 by 2 matrix G in GL2 of C such that, so we are identifying this vector space with C2, so that we are working with the matrices. So, if there exists some G in GL2 of C such that G S G inverse should be S dash and G T G inverse should be T dash. So, now we can actually see that, so this is a simple exercise. Whenever you have equation like this bracket ST equal to T, then T must be nilpotent. Actually, one can use the theory of Lie algebras. For example, if we take solvable Lie algebra, the least theorem actually says that so there exists a vector inside your vector space such that that will be simultaneous eigenvector for that action of the Lie algebra, that solvable Lie algebra. So, in particularly you can prove that there exists a basis of the representation capital V such that with respect to that basis all the elements of the Lie algebra will be represented as upper triangular matrix. So, now if you have some element in the commutator, then you can easily see that that commutator element must be nilpotent, because both, like for example, for G2 it is non-abelian, but it is easy to see that this is solvable. So, in particularly this S and T. So, let us say you have a representation. So, let us make it precise. So, if I have a representation of G2, let us denote it by phi. So, V is any finite dimensional representation. Okay. So, then using Lee's theorem, one can actually get a basis of capital V. With respect to that basis, all the elements of G2 will be represented as upper triangular matrices. In particularly, when we take this phi of S, phi of T, which is going to be equal to phi of T. So, that implies actually phi of T is nilpotent, because it is commutator of two elements, both are represented as upper triangular matrices. So, that forces that phi of T must be nilpotent. So, that is what happens here as well. So, we can actually immediately conclude T is nilpotent, but this is something one can prove without using the Lee's theorem. So, let me give you the give you a quick proof. If S and T is equal to T, then that would imply that trace of T must be 0. So, there is a trace criterion. Suppose you have a operator which is acting on finite dimensional vector space V, then N is nilpotent if and only if trace of n power k is 0 for all k greater than or equal to 1. So, one can prove this using Van der Waals matrix. Okay. So, determinant of Van der Waals matrix, we know that it has some specific form. Using that, one can prove this characterization. I will leave it as exercise. So, this is somewhat standard result. So, again this works for over any field, but we are actually assuming over complex number. So, we do not need to worry about the field. So, now trace of t is 0. What is about trace of t square? So, here is the simple computation. T actually is given by st minus ts. Now, t square will be t st minus st minus ts. So, t square is tst minus t square s, which is also same as st square minus tst. So, now if you add these two, then you get 2t square, which is exactly st square minus t square s, which is nothing but the commutator between s and t square, and this forces that trace of t square is 0. So, now you have trace t is 0, trace t square is 0. So, this suggests that 2t square equal to st square suggests that k t power k should be equal to the bracket s t power k. Let us use induction to prove this. Now, calculate that k t power k plus 1, which is going to be, this is s t power k minus t power k s. So, this is going to be exactly t s t power k minus t power k plus 1 s. Now, note that we already have t equal to st minus ts. So, t equal to st minus ts gives us that t power k plus 1 equal to s t power k plus 1 minus t s t power k. So, now add these two. So, you get k plus 1 times t power k plus 1 is equal to, so these two things get cancelled, s t power k plus 1 minus t power k plus 1 s. So, that means this term k plus 1 t power k plus 1 is nothing but the commutator between s and t power k plus 1. So, this tells us that trace of t power k plus 1 must be 0, because we are working over characteristic 0 field. So, that means trace of t power k is 0 for all k greater than or equal to 1. So, that implies t is nilpotent. So, this is some basic linear algebra fact. One can use Lee's theorem to give quick proof, and one can also prove it directly using this trace trick. So, now we want to understand like when one can actually get simultaneous G such that Gs G inverse is S dash and Gt G inverse is T dash. So, let us fix the tuple S and T such that this St equal to T. So, we define the relation as before. St is related to S dash T dash if and only if there exists G in GL2 of C. So, let us write it here. If this is the definition such that Gs G inverse is S dash and Gt G inverse is T dash. Okay. So, we are interested in actually parameterizing all these tuples, satisfying, let's write capital A to B the pair S comma T such that S T, the bracket is T. So, this condition should be satisfied. So, we are looking for the parameterizing set for this cosets. parameterizing set for this A modulo tilde. Okay, how one can actually get it? For example, what one can do? So, because this GL2C act on these tuples, one can without loss of generality assume that S is in the Jordan canonical form. Okay, sorry, one can actually just assume T is in the Jordan canonical form. So, now if you take nilpotent matrix, so then if T, the Jordan form corresponding to T must be just this 2 by 2 matrix 0 1 0 0. So, this is the Jordan form that corresponds to T. So, in particularly ST, this tuple related to S dash, which is GG inverse, comma 0 1 0 0. Okay. So, let us determine very explicitly what happens to this. So, now we have that ST is equal to T. Okay. So, without loss of generality, so we can work with this as S. So, we can assume T is of the form 0 1 0 0, because T is nilpotent up to the GL2 conjugation. We can actually take T to be this 0 1 0 0, no issue. So, now if T is 0 1 0 0, so then ST being equal to T tells you that 0 1 0 0 is exactly equal to the commutator. Let us say S is some A B C D, then this is A B C D comma 0 1 0 0. Okay. So, this is what you get, and a simple calculation indeed tells you that. So, this force, so if you calculate this commutator, so this actually forces 0 1 0 0 is exactly equal to minus C A minus T 0 C. So, this is just computing the commutator of these two. The commutator of these two is exactly equal to minus C A minus T 0 C. So, now this tells you that C must be 0 and A minus D must be 1. Okay. So, this means D is equal to A minus 1 and C is 0. Now, what we are going to do? So, we are going to actually use this in the matrix capital S. So, then S is of the form, you can see that C is 0 and then we have A minus 1 and then B is there 0. So, this is the matrix that we are getting, and T is 0 1 0 0. Okay. So, now we are looking at this possibility. So, what is about once we have something like this? Okay. So, for given let us say A comma B, which is complex numbers. So, one can define this representation pi A comma B from G2 to GL of C2 such that, so this small s goes to A B 0 A minus 1 and then T goes to 0 1 0 0. So, then I will leave it to you to check, okay, that pi A B indeed defines a representation of G2. Okay. So, it is a simple calculation. Basically, what you need to check? You need to check that the bracket S T is T, where this is S and this is T. So, given A comma B, so we are able to actually get a representation. So, now this general discussion actually tells you that given any two dimensional representation can be parameterized by this a comma b. But there could be some of them could be isomorphic to each other. Okay. So, it can happen that pi a b is isomorphic to pi c d. Okay. So, we have to determine when that is going to happen. Okay. So, let us analyze. So, pi a b is isomorphic to pi c d. So, then if and only if again there exists some g in GL2 of C such that g a b 0 a minus 1 g inverse is going to be c d 0 c minus 1 and g 0 1 0 0 g inverse. So, that is going to be 0 1 0 0. Okay. So, because we have already assumed that without loss of generality t can be 0 1 0 0. Now, up to this equivalence relation. So, if pi a b is actually isomorphic to pi c d, so then this is what we will have. Okay. So, now let us call this is equation 1 and call this is equation 2. So, one can easily check that equation 1 gives us that the tuple a minus 1 should be equal to the tuple c minus 1, because both these matrices should have same eigenvalues because they are conjugate. Okay. So, since both the matrices have same eigenvalues. So, conjugate matrices will have same eigenvalues. So, they are conjugate. So, they must have same eigenvalues, and eigenvalues of a b 0 a minus 1 is a minus 1. So, this implies actually a equal to c. Okay. So, now what's about equation 2? So, this is actually a simple calculation. So, maybe we will leave it as exercise. So, the equation 2 actually tells us that g can be only of the form alpha beta 0 minus alpha, where alpha is actually invertible complex numbers and beta could be any complex number. Okay. So, basically one way to see this g commutes with 0 1 0 0. So, using that you can actually just prove that g must be of the form alpha beta 0 alpha. So, now if you put back this inside the equation 1, okay, because the g is of this form. Okay. So, now we can actually substitute this back to this equation 1, because equation 1 and equation 2 must be true simultaneously. So, if we substitute, okay, substituting g equal to alpha beta 0 alpha back into the equation 1, we get, this is again a simple calculation, because g a b a g a inverse a minus 1 g inverse equal to c d 0 g c minus 1. So, you can just do this calculation. So, this will give us that alpha b plus beta a minus 1 is equal to beta a plus alpha d, and which is true if we choose this beta to be just alpha into b minus d, and which is true if we just choose beta equal to alpha times b minus t. So, that means we are saying that whenever we take these two representations pi of a comma b and pi c comma d, they are isomorphic if and only if a equal to c. So, what we proved, pi a comma b isomorphic to pi c comma d. So, that is what we denoted. So, if and only if a equal to c. So, now what we can do, we can actually define this following map. So, if we take the two dimensional representations of G2 up to isomorphism or classes, let us say classes of V is a two dimensional representation of G2. Then from here to complex numbers, we can just define a map. So, pi will be naturally isomorphic to pi a comma b, then you send pi, given this pi, this value a. So, the way you get the value a is, look at the matrix capital S. Okay. So, that is what actually takes this form a b 0 a minus 1. Then we indeed prove that matrix, that operator S has two eigenvalues a and a minus 1. So, basically a will be the largest eigenvalue. Okay. So, what is the map? The map is defined to be, given a representation pi. So, we are mapping the largest eigen value of pi of s. Okay. So, this is the map that we are defining. Then it is easy to see that this gives us one-to-one correspondence, because pi a b is isomorphic to pi c d if and only if a equal to c, and given any a, we can actually look at that a minus 1 and then actually define these representations. Okay. Given a comma b, one can actually define these representations. So, this way actually we are able to actually produce this parametrizing set for these representations. Okay. So, this gives one-to-one correspondence between these two dimensional representations of G2 and this. So, this way we have classified all possible two dimensional representations of G2. So, you can see that the classification of the representations of solvable Lie algebra, that gets really very ugly. Okay. So, even classifying this two dimensional representations for this very small non-abelian Lie algebra G2 itself is becoming very hard. So, what we have actually proved using this equation, the bracket S t equal to being t, and the dimension of this space does not matter. So, we proved that t must be nilpotent, but if t is nilpotent, then the Jordan form corresponding to 2 will have like various choices when we increase the dimension. Okay. Maybe you take it as exercise and then see what are all the possible Jordan forms for nilpotent operators. So, when we take like n equal to 3, n equal to 2 and so on. So, then you have lots of choices there, and then like, so those choices will actually give you somewhat more complicated calculations to determine what is S. Okay. So, this gets really very ugly, but when we actually go to simple Lie algebra, so we have this root space decomposition of simple Lie algebra, which actually gives you what is called triangular decomposition. So, now using the triangular decomposition, one can actually develop this beautiful theory that was proposed by D. N. Verma. So, this highest weight theory actually kind of helps us to understand all possible irreducible representations of 5-dimensional simple algebras. Okay. So, at least in this course we are going to see that for SLN, and then we will use SLN representation theory to understand the representation theory of GLN. Okay, I will stop here. We will continue with more representation theory in the next class. Thank you.